Hello everyone, this video is about Rocket to Mars brought to you by Group 1. It is noted that by 2022, Elon Musk plans to send humans or cargo to Mars but has failed miserably with repeated delays and countless setbacks in 2023 with SpaceX. Hence, it's our responsibility and passion to see the feasibility of using available rockets instead, like RocketLab by Peter Beck in New Zealand, which is far cheaper and nearer to our local country Malaysia. Our mission will be sending a lightweight but capable AI bot by itself to Mars to conduct a survey of the planet with 100% accuracy of how humans will have to deal with the reality in Mars. Introduction. A rocket's trajectory when flying to Mars demonstrates the principles of kinetics and kinematics. Kinetics is the analysis of forces which causes motion. Kinematics, on the other hand, is the study of the geometric aspects of motion. In this video, we will be looking at the kinematics of finding maximum height and rotational motion of the rocket.
Rectilinear motion is the term used to describe a particle's movement when it is limited to traveling in a straight line. The particle's displacement and its derivatives, such as its velocity and acceleration, are all one-dimensional vectors. Continuous motion. The coordinate axis S determines the route that a particle takes when it moves in a straight line. The position vector R, or the scalar S, determines the particle's location at any given time with respect to the origin O. There are positive and negative scalars. Erratic motion. When a motion parameter such as S, V, or A is not continuous or the function exhibits leaps or abrupt bends as seen in the figure, erratic motion results. You must examine each continuous section of irregular motion independently while analyzing it. When a particle travels along a curved path. The curved path can be in two dimensions, in a plane or in three dimensions. The figure shows a rectangular component. The position of the particle can be defined at any instant by the position vector. R is equals to x into I plus y into j plus z into k. The magnitude of the position vector is equals to r root over x square plus y square plus z square. The direction of r is defined by the unit vector.
So using projectile motion, we will be able to find out two types of motion, which will be in components. So there's horizontal component and vertical component, which denotes as x-axis and y-axis respectively. And now onto nominal and tangential components. We know that any acceleration of a particle, we do not have a linear motion as speculated in real life. So we definitely have tangential coordinates that we have to find out in order to determine the actual velocity of the particle when traveling in nonlinear motion. It's understood that the foundation of kinetics involves Newton's second law, which, as we can tell, it's a force over equals to mass times acceleration. Hence, we know that in order to find acceleration, we know that force is proportional to the acceleration of it, which is the net force, and whereas the mass is inversely proportional if you do it by the example of force over mass equals to acceleration. So, what are the application examples of Newton's second law of motion? In various fields of engineering, physics, and sports is quite useful. In fact, we do study them in increasing the performance of certain criteria needed for using kinetics and the study of motion of objects. So the example that we can tell from on our right side where there's a rocket, where the force of a rocket is determined by the mass of the body as well as the acceleration of the body. And in this case, in order to find the acceleration of the rocket, we must first find out the force, or known as the thrust, that the rocket is producing.
An object's highest vertical position along its trajectory is its maximum height. Only the vertical component of an object's initial velocity affects it. At the maximum height of an object, the vertical velocity is equal to 0. Now, in order to find the maximum height of an object, we can use these basic kinematic equations. Now let's move on to rotational motion. Rotational motion refers to the motion of an object around a circular path in a fixed orbit. It only takes rigid bodies into account. A rigid body is an object with a mass that maintains a rigid form. We can calculate rotational motion using these equations. A rocket's vertical trajectory can be described by its state variables, which are altitude, velocity, and total mass, each with respect to time. What is a trajectory? Simply put, trajectory refers to the path of a moving object which is traveling through space as a function of time. An example would be a rock that is thrown upwards. The path of the rock is the rock's trajectory and can be determined by the gravitational forces and air resistance acting upon it. A real-world application of kinematics is finding the maximum height and rotational motion of the rocket by using its trajectory. This image shows an example of a rocket's trajectory.
So now we move on to the whole process of a rocket getting to Mars. Its motion consists of five main stages. We begin with the first stage, which is the liftoff of the rocket to reach the Earth's orbit, and we utilize its thrust and its complete mass to calculate for the total force applied to it. And to the total force that we obtain, we can find its acceleration, which in this case is 7.444 meter per second squared. For this case, we assume the liftoff of the rocket to be completely vertical, going up to go against the gravitational acceleration of the Earth. And in this case, our final result proved that it is accelerating upwards at this magnitude. And next up, at the time of t equals 153 seconds, is when the main engine of the rocket cuts off. We can utilize one of the motion equations as shown here to find its final position at that time. And in this case, we found it to be 87.126 kilometers up from the surface of the Earth during this time of 153 seconds. Other than that, the work done in the first stage of the rocket motion can also be determined as follows, whereby we multiply its thrust and its distance from sea level during separation, which is obtained beforehand here, to find its work done in energy form.
Alright, on to the second stage, reaching the escape velocity of the Earth. To obtain the operating speed of the rocket, 87.1264971 km after main separation, the following conditions are utilized. Given that the second stage remains within the Earth's gravitational force, hence the centripetal force acts as the force that equalizes the thrust of the rocket. According to the calculation below, we know that the thrust will be around 26 kilonewtons, and it is calculated that the velocity takes is 7,856 meters per second. Next up, the rocket proceeds to fly away from orbit to Mars. The second stage allows for the usage of all available fuel for 5 minutes to do so. Using the speed from the point of orbit at 7,856 meters per second, we can deduce the final speed of the rocket by finding its acceleration in the second stage. It is also known that an escape velocity of 11,190 meters per second is required. Hence, the backup solution of using gas thrusters is utilized to boost it to the desired level. So according to the calculation below, we were able to calculate that the additional kinetic energy required will be around 74 gigajoules. Alright, for the third stage, the journey to Mars away from Earth. From Earth orbit to Mars orbit, the journey is assumed to be a straight line with an average velocity maintained across the whole journey. The distance between Mars and Earth is utilized along with the average velocity of the rocket in order to find the time taken to complete the whole journey. So the distance, according to the equation, is 54.6 times 10 power 9 meter, and the velocity is 11,190 meters per second. So if you take that and divide by each of them, we will get 56 days. In this case, the distance between the Earth and the Mars is given as 54.6 times 10 power 9 meter, and the average velocity given is the velocity of the rocket as determined in the previous stage, which is 11,190 meters per second, or in simple words, escape velocity of the Earth.
After having traveled a long distance from Earth to Mars, the second stage will require deorbit by decelerating its velocity from 11 kilometers to 5 kilometers per second. Hence, it will take about 2 minutes of time to decelerate since the AI board has a thrust of ionic thrusters that can generate 2 kilonewtons of force. And knowing that the AI board has a mass of 40 kilograms, hence we know our acceleration. By using acceleration, we can determine our time. So in summary, we know that by having the mass of the board and by using gravitational constant of mass, which is 3.71, we're able to find out the total force required to land the AI board. This is also assuming that everything is in rectilinear. And hence, thank you for watching.